Hello, and welcome to episode 6 of the Staff Spotlight video series. Today we'll be interviewing Brian Duff, the Demonstration and Deployment Program Manager for the Bioenergy Technologies Office. Mr. Duff is a biochemical process engineer with 30 years of experience in biotechnology and renewable energy. Mr. Duff will be interviewed by Liz Moore, a technology manager for thermochemical conversion activities, who has been with the office since 2009.
Hi, Brian. So what is your role in the Bioenergy Technologies Office?
Well, thanks for asking, Liz. My role in the Bioenergy Technology Office, its current role is as the program manager for the Demonstration and Deployment Subprogram. I was originally hired by ERE to be the chief engineer for the Biomass program, but I inherited the lead role for Demonstration and Deployment when my predecessor left for another job at DOE in the Loan Guarantee Program. So as program manager for a demonstration and deployment, which we call D&D, I'm responsible for overseeing the office's portfolio of integrated biorefinery projects, and this includes a set of 21 competitively awarded projects, as well as a comparable number of congressionally directed projects, or what we call CDPs. So in the D&D subprogram within Bioenergy Technology Office, we primarily manage the conduct and performance of the integrated biorefinery projects. And these are generally associated with the scale-up of integrated process technologies, beginning at the pilot scale, moving up through the demonstration scale, and occasionally into the commercial scale production. And the real distinction between our D&D projects is that all of the IBR awards invoke large capital awards, like large dollars, and they also invoke an element of process design and engineering, equipment procurement, construction, commissioning, startup, and then operations. And due to their larger scale and their larger cost and the construction element, and also their focus on process demonstration and validation, we manage these projects are considered demonstration and deployment, so in the essence of what we call market expansion. And because of their size and the special set of conditions of these, we use a special set of DOE management practices that are normally reserved for large capital infrastructure projects like building buildings. So within DoD, the integrated pilot means it's the first time that all the unit operations going into producing a product from like the feedstock through to the final product or fuel is linked together in one place. And the integrated pilot is used to validate the integrated process performance, and the goal is to confirm the conversion efficiency and to collect the data that is going to be required for the next step in scale up. So this data coming out of the integrated pilot is really required and essential to coming up with the equipment specs that are required for the larger pieces of equipment that would be in the next step of scale up, which is demonstration scale, or what some people call a semi-works plant. And again, we do these activities in the integrated pilots and the integrated demos because what we're trying to do is buy down the risk, both technical and financial, so that eventually the private sector finance community come in and replicate these first-of-a-kind plants. And it's a real challenge because the venture capital community and a lot of technology developers, project developers, they want to skip the demonstration phase. They want to go straight from, a couple, half a ton a day. They want to jump right to 2,000 tons a day. And by skipping the demonstration scale, their odds of success are infinitesimal. And so I think this is the role where DOE wants to get involved, and that's what the purpose of D&D is to really help these companies fund the demonstration scale plant, because these demonstration scale plants might cost 50 or 100 million bucks. They take like 3 years. Often you use the plant for 6 months and then shut it down, so it's like a stranded asset, and no venture cap or financing bank is going to stand for that. So I think this is the role where DOE's Demonstration and Deployment Group really has a role, because we're trying to get these technologies that are emerging across the so-called valley of death, and that's where the financing runs out, and they can't get through the steps of scale up to the actual first-of-a-kind plant, and it's going to take more than one first-of-a-kind plant. The financial community, the debt financing community, they want to see as many as 3 or maybe 6 plants before they feel comfortable enough to put the loan down and feel comfortable they're going to get repaid. So that's really what the DOE is doing with their demonstration and deployment projects. And then lastly, as the program manager for demonstration deployment, I actually supervise a team of technical project officers like yourself who perform the day-to-day project management of these integrated biorefinery projects in the Bioenergy Technology Office portfolio.
So prior to your role here, how did you get started in the biomass technology field in the beginning?
Sure. My interest in biomass utilization really grew out of my dedication to the field of biotechnology. I've always been interested in biology, and my first bachelor's degree was in biology, and it was really sort of karmic. But my first job out of college was as a lab technician for a company called Syngas, and in 1977, Syngas was probably the world's original and first real biotechnology company. In fact, at that time, biotechnology hadn't even been coined as a term yet. It was still being called bioengineering. So I got this job as a lab technician at Syngas, and Syngas was formed by a Nobel laureate and physicist from UC Berkeley called Donald Glasser. And Glasser had invented a high-throughput screening and mutagenesis system and a device for improving the performance of microorganisms in fermentation. And the system that he invented actually predated our modern molecular biology, and it predated genetic engineering. So it used conventional mutagenesis like chemicals and ultraviolet light, and then we would screen thousands of strains for improved performance for various clients like Hoffman, LaRoche, and other pharmaceutical companies primarily. But actually, one of the projects I worked on in 1977 was for the Brazilians to improve an enzyme called cellulase. So I've actually been working on cellulase since 1978. And so while I was there, I was really inspired where I met a couple of my mentors. I was really inspired by what was going on at Syngas and really the potential of biology to improve all of our lives, our quality of life. And an interesting side note is it was at Syngas where one of my colleagues invented the polymerase chain reaction, the PCR, which has actually made the entire human genome and molecular biology as we know it today possible. Without PCR, it wouldn't be happening, and that was invented by a guy in the lab next to mine. So another interesting thing is this was all going on during the first gas crisis in the mid-'70s, and I got it in my head I was going to dedicate my career to what was at the time called bioengineering, and subsequently became called biotechnology, and I decided to devote my career to it and applied to grad school with the goal of combining biology and chemical engineering. And in fact, in 1978, in my essay for entrance to grad school, I actually put as my goal I wanted to put the oil companies out of business using biology, which I've subsequently toned down and come to realize that we really need the petrochemical companies. They're our friends. They're central to our mission, and they do a lot of good things for society. So I no longer want to put them out of business, but I do want to replace a lot of their products using biology. Subsequently, I did go to grad school, and I did get a master's degree in chemical engineering, and I went on to become a fermentation scientist. And one of my first jobs out of grad school was for Pfizer, and I was doing screening for new antibiotics using conventional mutagenesis. And then I also, one of my next jobs, I worked for an ag biotech startup where I was responsible for scaling up recombinant DNA bacterial products and processes. So my career goal sort of evolved from being a fermentation scientist into doing process design and engineering for recombinant processes and products. And my goal became to learn how to design and construct the new generation of manufacturing facilities that would be using these genetically engineered microbes to produce all the food, drugs, and chemicals that we need to maintain and enhance our quality of life, especially in the face of a huge burgeoning global population. So I still see GMOs and as one of our primary tools in feeding and maintaining the health and quality of life of everybody on Earth, not just the U.S. So I joke it's my mission. It's like the Blues Brothers. I'm on a mission from God,
Right.
And that's really what brings me to the biomass. Is in 1991, NREL was looking for someone to design their lignocellulosic PDU, which was going to be used in a recombinant organism. So I was recruited by NREL to design and construct and operate the lignocellulosic process demonstration unit, and at the time I didn't really care or know anything about ethanol. I really just wanted to learn how to design these manufacturing facilities and containment systems for GMOs. But as it turned out, I got bit by what I call the biomass bug, and it resonated with my interest in biotechnology, and I got off on what I call the environmental biotech tangent that I've been on for 25 years now. And so here I am in biomass, and I still believe and am dedicated to utilizing biotechnology and GMOs to sustainably produce all the fuels and products, including fuels that our lifestyles require, and not just for us, but for everybody on the planet, because it's becoming a global sustainability issue.
Thanks. So over these 25 or so years that you mentioned, you've watched a lot of technologies develop. What do you feel is the most promising technology right now?
Well, I'd have to, actually, I'm going to limit it to biomass, but I think the most exciting thing I've ever heard of is using DNA as a digital storage device, and they can fit all the information that's required by the planet for a year in less than 4 grams of DNA. It's truly amazing, so I suggest people take a look at that. But in the context of the Bioenergy Technology Office, we work in 2 areas, biochem and thermochem. And so I really have one or a couple of each. And the first is really basically due to my training as a fermentation science. It's in the biochemical area, where I see just an outstanding opportunity and potential for using these naturally occurring and potentially as yet undiscovered microbes, as well as GMOs, to manufacture just a huge and growing array of products, including fuels, on a sustainable and carbon neutral basis. And this is really derived from 2 areas that the Bioenergy Technology Office is working to develop, and one is really low-cost cellulosic sugars, and the other is bioproduct fermentations. And in the first case, I really truly believe we can achieve cost-competitive sugar production from cellulose at or below the cost of cane or corn sugar from cellulosic biomass, including trash, including MSW, and with low-cost cellulosic sugars, the door to fermenting bioproducts is really wide open. And I really see the U.S. having an opportunity to be the global leader in sustainable bioproducts and biofuels, and really to rebuild our outsourced chemical manufacturing base, which has deteriorated to next to nothing. And so in terms of jobs and economic development, I see the entire biomass to bioproducts realm as a place for rekindling our economic dynamo and creating jobs and increasing sustainability and reducing greenhouse gases. And the reason I say that is because the U.S. is really the biomass king. It's not because we have more biomass, but it's because of our agricultural sectors, the leading in the world. We have more agricultural residues than anybody. We generate more trash than anybody. And we also have a centuries-old wood basket that's diverse across the entire regions of the country. So we're in the best position of anyone in the world to really capitalize on biomass utilization for fuels, chemicals, and products. And really, I'll tell you in a minute, food too. So on the thermochemical side, I see a number of outstanding areas of potential, and the one that really intrigues me the most right now is the area of what we call syngas fermentations. The Bioenergy Technologies Office is sponsoring INEOS, which is a company using a naturally occurring strain of microorganisms that ferment syngas, basically carbon monoxide and hydrogen, into cellulosic ethanol. Now, INEOS is using gasification of MSW, trash, and green waste to convert syngas into cellulosic ethanol. It began operations this month. And at 8 million gallons, it will be the first cellulosic commercial scale plant in the United States, and it'll be generating cellulosic ethanol this year. There are other companies that are pioneering in this area, and a couple I'd focus on are not in our portfolio, but one is called LanzaTech. They're out of Chicago, and the other is called Caverity, and Caverity is located in Berkeley, California. LanzaTech utilizes syngas and exhaust gas, not just from biomass gasification, but they can also use exhaust gas. Right now they're using exhaust gas from steel mills in China, and their organism will ferment the exhaust gas or the syngas into fuels. And what they've done is they've engineered the microbes to make cellulosic ethanol, as well as a growing array of bioproducts, including butanediol and some other more valuable specialty chemicals. So with their genetically engineered platform organism, they have the potential to generate a slew of what used to be petrochemical chemicals, specialty chemicals, but using waste exhaust gas from steel mills and potentially coal plants. Coverity has another almost more interesting but similar business model, except their microbe vector, their engineered microbe, produces lipids instead of ethanol. And their molecular biologists are able to engineer the organism to utilize the syngas from biomass gasification to produce huge and a growing array of lipid products. And so, and then these lipid products can be converted into renewable hydrocarbons like diesel or jet, but they can also be used in things like cosmetics, and they can also be used in other applications that have historically been addressed by petrochemicals or plant oils. Theoretically, and it's actually becoming real, a syngas fermenting microbe could actually be producing omega-3s that you might buy at Vitamin Cottage and other nutraceuticals. So imagine being able to make a food supplement from a gasified trash or a gasified tire. I can envision a day where pharmaceuticals and even food proteins are being made from a tree or a tire or even the exhaust from a coal-fired power plant. I mean, imagine making protein for our cattle and our pigs and swine and poultry, or even ourselves, from gasified trash or from a coal-fired power plant. I mean, making food from a coal-fired power plant, that's outrageous. And I just think that's incredibly, empowering and exciting, and part of it's due to because the work that the Bioenergy Technologies Office has done in supporting biomass gasification as well as the development of these syngas fermenting organisms.
Great. So that's your vision for the whole industry. What is your vision for the demonstration and deployment platform?
Well, I see for our demonstration and deployment, or our D&D subprogram, I see us continuing to be sort of the exit point for the R&D pipeline. So new concepts come into the R&D pipeline, maybe from Office of Science or maybe the private sector, and then we help support their development as they scale up, and then they pop out into the scale-up realm where demonstration and deployment is required, and assistance to get across the so-called valley of death. And I see that as really our niche, and I see it as a vital niche that we need to maintain funding on. And I think I also see us continuing to focus on fuels, but with an expanding role in products, because actual fuel is a subset of products, not the other way around. And so anything we do to promote products is going to eventually help bring us down what we call the learning curve for fuels. And so I see our focus to remain on liquid fuels. Even if the light duty fleet becomes electrified, we're still going to need diesel and jet for our commercial vehicles, for our truck system, for our rail system, for our aviation system, for defense. We're going to be burning liquid renewable diesel and hydrocarbons well into 2050. So it's not going away anytime soon, and I think our role is going to persist. So I see us doing additional projects with the technologies that are currently in our portfolio, but I also see us expanding our portfolio to accommodate these new technologies that are coming out of the R&D pipeline. And I also see an enormous amount of really innovative and maybe unanticipated technologies that are coming out of programs like DARPA and ARPA-E. And I've just recently started calling these biomass mimicking technologies. They might not actually use biomass, but they're focused on liquid fuels. So maybe our Bioenergy Technologies Office becomes more embracing of in quotes, outside the box technologies. So for instance, there's a technology being developed at one of our national labs that uses a nanochip to fix carbon dioxide using sunlight. And so we're basically talking sunlight to fuels using a chip with no organism. So it's mimicking both photosynthesis as well as the biofuels production. There's also a Navy-sponsored, a Defense Department-sponsored project that has a technology that actually harvests dissolved CO2 from seawater in the form of carbonates and makes it into fuel. And so we're talking seawater to fuels. It's amazing. As the pH of the ocean goes up because of the CO2 level, the idea of actually harvesting some CO2 out makes a lot of sense. But So the emphasis there is really on liquid fuel. It's not a biomass, it's not an organism, but it's electrochemical process really. There's also the electrofuels, which came out of RPE. There are organisms involved with electrofuels, but there's also electrochemical cells that don't use microbes that can actually fix carbon and lead to renewable liquid fuels. There's also things like artificial leaves. Again, it's a biomass mimic. It's not going to use an organism or a living thing or maybe even an enzyme, but it's going to in one way or another make a liquid fuel. So I don't see any problem with EERE maintaining our role in demonstration and deployment for quite some time, and I think it's going to be vital to meeting the challenges of the next couple decades.
Agreed.